Hello, folks. The Big Bang Theory may be wrong. The James Webb Telescope has provided evidence that sheds doubt or further doubt on the Big Bang Theory. Remember, it's always been a theory, not the Big Bang facts. I've never really liked it. Too arbitrary. It was difficult for me to be okay with the notion that there was nothing, not even time, not even space, nothing anywhere. There wasn't even anywhere at all. And then, pow, time and space just happened. I got a problem with it. And for a while, I guess it was the best theory. I mean, it may still be the best theory. But there were problems with it, pretty massive problems. And now this James Webb Telescope has provided troubling evidence for the theory. And we're going to start and talk to Professor Doug Arion, who is a physicist, an astronomer, and much more, worked in, well, defense for a long time, but that's not what we're dealing with here. He's going to first explain how the James Webb Telescope is different and how it could provide this information. So, Doug, thanks for being with us.
It's great to be with you again, Bradley. These conversations are always great. So just a reminder to everybody about James Webb. I'm sure you've all heard of it, but what makes it different? And that difference is what lets us find these new things that make us, confused in a good way, right? That's how science progresses. So a couple of key things about it. The first thing is it's big. So compared to even Hubble, it collects a lot more light, so it sees a lot farther. But the second and most important thing about it is that the light it looks at is light that we can't actually see with our eyes. It's infrared light. It's the light past the red. And say, okay, why do you care about? Why would you want to look at that, right? So there's several reasons to look at that. Firstly, remember, all things in space glow at many different colors. Our eyes just happen to see a few of them. But the other thing is the universe is expanding. Okay, that we know, that's an absolute for sure. We know that the universe is expanding. And that was the first hint that there was a Big Bang, right? That the universe is expanding. And because of that, when you look at things that are very far away, you're looking very far back in time. And between then and now, the universe has expanded and that light has been stretched. So the light that you'd normally see, kinds our eyes can see, has been stretched to the point that it's now infrared. It's longer than stuff that we can see. So
can you talk a little bit more about how it's stretched? What does stretch mean? There's more distance between the photons or something like that?
Well, remember, light behaves as a wave, right?
Yeah.
It goes back and forth, right? So imagine you take a piece of flexible paper and you draw a wiggle on it, and that's the wave. And then you stretch the paper. That wave gets longer.
Okay.
What's happened here, right? That light has been traveling, and as it's traveling, space is stretching as space gets bigger. And that means that stuff is now longer than it was before. So if we want to look at the stuff that's really, really early, right? Looking back towards the Big Bang period, all of that has been stretched. So fantastic telescopes like Hubble, I think Hubble's a fantastic telescope, can't see that. Its eyes are like ours. It's cut off. It can't see into that infrared. Webb was built specifically to look at the infrared, and that's for really several projects. One is the one we're talking about today, the early universe. The second one is how galaxies form. We're going to look at some of those pictures in a couple of minutes. They're gorgeous pictures. And a third one is to look for planets, because planets glow in the infrared. So that was the reason it was built and why it can do those things and nothing else can. And until you go to use it, you don't know what you're going to discover. And so we discover some new things. So that gives you a quick idea of why Webb is important and why it's so different, and therefore why you find something new because you didn't have the ability to do it before.
Okay. And so how did what the Webb telescope has seen cast doubt on the theory, the Big Bang Theory? What did it see? Did it see that space wasn't expanding like they thought?
No, the space is expanding as expected, but what we have found, and I'll show you some pictures in a couple of minutes, is this. So you can look back in time and you say, okay, when the universe was a baby universe, it's only existed for a certain amount of time. So only things that can happen in that length of time should be able to happen. We can look at you and we can say, okay, Bradley, you were born at a certain point. By the time you were 3 months old, we expect you to look like something, to weigh so much, and be able to do these things. And by the time you're 3, and by the time you're 6, and by the time you're 10, and so on, right? So, if you see a kid who's 4, you expect that kid to be walking and running just fine. But imagine you found a kid who was only 3 months old, just 3 months old, and was running around playing soccer as well as Lionel Messi, right? Running that well.
Yeah.
You would look back and you go, okay, something's not right here. So either mom and dad are lying about how old that kid is, or kids develop in a way that we don't understand, right? We look at that and go, no 3-month-old can play soccer yet. Here we see 3-month-old kids playing soccer. We don't understand how 3-month-olds develop. Well, that's the problem we have here with galaxies. You look back far enough, you go, we should be seeing baby galaxies. We should see galaxies that are still in diapers, right? And yet we see galaxies that are basically playing soccer. Things that are well developed earlier than we thought you could have them. So that means you now have to go back and go, okay, give me time out. I'm not understanding this anymore because I thought there wasn't enough time for this to happen. So that's the big thing, the really big thing that makes us all go, okay, we got to go back to the drawing board on some aspect of it. It doesn't mean throwing out the whole Big Bang. The whole basic cosmology picture still works, but there are obviously some details about the early universe where we go, things are developing faster than we thought. That's the big news. And it's actually a very big thing, right? To discover that galaxies are forming much earlier, full bore, real, growing, living, breathing, for lack of a better term, galaxies, earlier than we thought they could be.
Okay, I want to make sure I get this straight. So the James Webb telescopes saw that galaxies were forming earlier than we thought they could.
Right.
And tell me again how that tells us that the previous calculations about Big Bang were wrong.
So you start out with a set of calculations. You say, okay, given the amount of energy and the type of energy early in the universe, which we can measure, that's the cosmic background radiation, right? We can actually measure that energy. You say, okay, let's work forward and say, as it cools, as the universe expands and cools, it's going to turn itself into stuff, into matter. And then gravity is going to pull that matter together and make stars. And those stars are going to accumulate into a galaxy. How long does that take? And you work out how long that takes. And you write that number on the board. Then you go out and you go look. And until the Webb images, earlier images said, that seems to work fine. We look back far enough, we see galaxies. Well, we expect to see galaxies. Okay, we're happy. Now Webb is looking earlier and going, wait a minute, we are seeing galaxies early. So we have a calculation that says takes this long and we shouldn't see them till here, but they're showing up here. They're showing up earlier. And so there's something in the model that's wrong. We don't know what it is yet. People much smarter than me. I understand this. I can talk about it. I can read it, but I'm not an early, universe cosmologist. Those people are back at the drawing board going, okay, how can this happen? And
Wow.
We don't know the answer to that yet, which is why it's fun and interesting. We just don't know yet. We have to figure it out.
We have a question from Joan, which is related to spectrography. Do other countries or U.S. have instruments that detect other aspects of the light spectrum? And if yes, what would that add to our knowledge?
So yes, there are all sorts of instruments on the ground and in space. So Hubble can look at light we can see plus into the ultraviolet. There's a spacecraft called Chandra that looks at X-rays. There's a spacecraft that looks at gamma rays. There are radio telescopes that look at radio, stuff that's past infrared, that's in the microwave and the radio. And of course, we have Webb that's doing infrared. So we look at all these different colors of light. Again, if you look at the very, very early universe, it's all infrared and radio because it's been stretched so much. But there are all sorts of other things, big explosions, the hot gas around black holes, for example. We look at that with X-ray telescopes because it's so hot, it's glowing in X-rays. So yes, we use all these different colors to look at everything. And in fact, some of the images I can show you here are overlays. We say, okay, here's what Webb sees, here's what these other instruments see, and we can put them on top of each other to try to understand what's going on.
It's a good time for me to bring up something I thought of when you were talking about infrared. I wonder, and this is beyond the scope of our conversation, unless you know the answer right away. How or why did animals and humans evolve to see the visible light spectrum, or the one we do see, rather than the others? I wonder how that evolutionarily benefited us. Why can't we see infrared? That might have helped out somehow.
That is a brilliant question, and I do know the answer.
Oh,
Here's
good.
something totally amazing.
Good.
It's something I heard. I learned this in the last couple of years. It's really amazing. All life on Earth started in the water, right? We started deep in water.
Yep.
Of all the possible colors, all the way from gamma rays out to radio waves, the only stuff that goes through water, the light we can see. All eyes developed. All of vision is in what we call, quote, visible light, really kind of redundant name, right? Self-serving name. This is the light that was able to penetrate deep into water. That's it. That's what we're sensitive to. So that's why our vision, why we have a thing called vision that's sensitive to light that's between, blue and red. And we can't see on either side, and we can't see radio waves, and we can't see X-rays because those don't go through water. Wow. Isn't that amazing how the biology connects to the physics, connects to the universe? And that means, by the way, that having a star like the sun that puts out most of its energy right where we can see is connected to why we have our kind of life here on this planet.
Man, I love that stuff.
Isn't that great?
It is. So before this Webb telescope discovery, or the discovery made possible by the Webb telescope, there were other problems with the theory. For example, the matter-antimatter problem and a couple of others. Mm-hmm. Can you talk about that a bit?
Sure. So, the overall picture of having an inflationary universe, right? Starts small, grows very, very rapidly, and then grows more slowly, and is now accelerating. That's our basic picture of the universe. And that basic picture explains a lot of things. It generally works. It's consistent with lots and lots of observations. So it may not be perfect, but it's not totally wrong, right? It works with that thing. But then we have these outstanding questions. You go, okay, if the universe started out purely with energy, hey, wait a minute, that works. We can look at it, we can see it, we can measure it. So we know that's there at that time. That energy should then condense and become matter. But that matter should be equal parts matter and antimatter, right? You take a chunk of energy, you get a positron and an electron. You get a neutrino and an interneutrino. But guess what? You and I are made out of matter, and there isn't much antimatter around. We have no idea why that is. So there's definitely a Nobel Prize or 2 or 3 waiting out there for one of your listeners who comes up with the idea of what happened to the antimatter? What is it about the early universe that made matter more common than antimatter? We don't know. So that's a definite problem, if you wish, about our understanding of early universe cosmology. So that's one of the very big questions, how could that happen?
While we're on that, what is antimatter? We know what matter is. You look at it, you break it down molecularly and then atomically and subatomically.
Right.
But what is antimatter?
So for every particle that you're used to, protons, electrons, neutrons, muons, all of those, there is another particle out there, behaves the exact same way, except its electric charge is opposite. So you have a positron that looks just like an electron, but instead of being negatively charged, it's positive. There are things called antiprotons. Proton, big positive charge that makes up most of your body, right? All the protons in the nuclei make up your body. And there are things called antiprotons. And here's the thing. If you put them together, if they meet, they annihilate. They disappear and pure energy comes out, matter, antimatter, which, by the way, was the idea that Gene Roddenberry had for how you could have warp drives in spacecraft. It doesn't really work, but it was a conceptual thing. Well, matter and antimatter make lots of energy. Okay, we'll have our engines based on matter and antimatter. It was a really good idea.
So how come you don't have anti-rocks? Why can't you build things out of the oppositely polarly charged particles? How come you don't have the opposite rock, an anti-mouse?
Right. Well, the thing is, At the atom level, you can. So in the lab, people have made antihydrogen. An antihydrogen has an antiproton with a positron going around it, and you can make this stuff. The trick is, remember, if antimatter touches matter, it blows up and goes away. So you can make this for a short time, hold it in a magnetic field, but as soon as it gets near anything else, poof, it goes away and the energy comes back out.
It's interesting that the winner of the battle is matter and not antimatter in that battle every time.
Well, the winner of that battle, the matter-antimatter, is energy, just the energy.
All right.
But what you're saying is correct. Early in the universe, the battle between matter and antimatter is there was matter left over. So it actually doesn't take much of an imbalance earlier.
Oh, I see.
Matter and antimatter cancel out, but there's still some matter left over. So we only have real rocks, right, and real mice.
Okay. So,
but in principle, you could make an antimatter rock if you could get enough antimatter together and not have it touch anything else.
So there's a whole lot of antimatter, but there's more matter. And where there's antimatter and matter together, they kind of cancel out. And what's left over is matter, and that's what we're made out of.
That's right.
Okay. Very good. Now, back to Big Bang. Does science ever ask why? Why then? Do they bother to ask that?
Sure. Absolutely. I mean, we don't have any answers to that. We certainly ask those questions. In fact, that's what drives it is, okay, here's the sequence of events. Well, okay, how did that happen? Why did that happen?
Mostly why? Like, why then? I'd be more comfortable with forever expanding and then contracting and blowing up and expanding again and contracting and blowing up again. I'd be more comfortable with that than just the idea of nothing. I have trouble with the idea of actual nothing, no time and space.
Right.
I guess that's,
yeah,
because I'm a rookie in the field.
It's not just rookies, it's the established veterans that have the same problem. And that's what leads to some of these alternative approaches, the approaches that there are essentially an infinite number of universes. There are universes continually popping out everywhere, and we happen to be in one. We can never observe any of the others because we're in our own universe, but there are lots of universes out there. That's really, I mean, in its way, that's almost as hard to stomach as something coming from nothing. When you have zeros and infinities never feel good, right? Something from nothing or an infinite number of everything. So those are hard to stomach. This idea of what's called the many worlds theory of like, okay, there's just an infinite number there, and we just happen to be living in one of them. But I mean, how else do you approach the problem besides throwing out these ideas and then saying, well, how would you know? That's a good question.
Right.
Great question.
The idea, maybe the thing that, well, maybe nothing is not really nothing. You know how in a vacuum particles can pop in and out really quickly?
Right.
Maybe there's something similar. We think of vacuum as nothing, but it's not really because things are popping in and out. Maybe what everyone thinks was nothing, the Big Bang came from nothing. Maybe it's not nothing. Maybe there's some stuff that was there that we just can't comprehend or see or measure or anything.
Yeah. I think my favorite word in science is yet. I mean, the idea that, we don't know yet, right? I mean, it's not that things can't be known eventually. Maybe it might take an awful long time, but you're right. Maybe there was something there and we don't know what it is yet until we keep working at it. It keeps us going. There's always stuff to find.
Okay. So you have some images to show.
Yeah, let's take a look at those.
Do that.
And I'm going to share screen and I'm going to share this. So you should be seeing an image of a galaxy.
Let me bring that right up there.
So what's beautiful about this that NASA has done for us, so this is a galaxy and this is the image that Webb took. And what it did is they overlaid for part of it what Hubble sees. Mm-hmm. Okay, so now you can compare in this galaxy, for example, here's what the infrared looks like, and you see where all the dust is and all the star forming, and then we can go and say, oh, okay, here's where all the light comes from that we do see. And that's an amazing thing to be able to put these two pieces together. So this goes back to the question that your listener asked before. What happens if we combine things from all these different kinds of instruments? Beautiful example there of overlaying them. And
So
this
how far would that be across that image?
This is
Yeah.
about 100,000 light years. Okay, about 100,000 light years. So it would take 100,000 years from light to get from one edge to the other, and one light year is 6 trillion miles. So it's 100,000 times 6 trillion miles, roughly.
Light doesn't peter out. Like if you have, it makes it all the way across without diffusing, or could it
Right,
really?
yeah, right.
Or is that just the speed? You just go.
Right. It just continues traveling. I mean, the reason we can see this at all is that light left there hundreds of millions of years ago, has been traveling, and now it's reached us and it's continued to travel. Now, of course, it's spreading into all directions, so it gets fainter as you get farther away, which is why we need a big telescope. But light travels indefinitely unless something stops it.
Right. And you'd think that during all the distance, there'd be cosmic dust and solar wind and all kinds of stuff that would block the light.
Well, yeah, every bit of light you see has traveled through that entire period without bouncing into anything.
Wow.
Which is amazing. You know, it's incredible that it traveled through whatever dust was in the way, past each little atom that's floating through space, even made it, you know, all the way past all the stuff in our galaxy, in our solar system, to be captured by the telescope. Is really very, very cool. So I'll show you just one more example of this. So this is a stunning image. And this is what Webb sees, and that's what Hubble sees. So that bottom half there, that's the kind of picture you're kind of used to seeing, right?
Yeah. Mm-hmm.
But the ability of Webb to see all the dust and the star-forming regions in here is quite remarkable. So to go to what we were just talking about here, this is one of the early Webb images, and we'll just look at that for an example. But there are, many of these now and deeper. But when you look at these little squiggles, all those little squiggles are bits of light from galaxies that are way in the background and are therefore very, very old. Now, this particular picture here picked up some of those distant galaxies. In fact, at the time, the most distant, therefore oldest versus earliest in the history of the universe objects that we had found was in these images. But let's see if I can find the one that I'm looking for. Actually, I think it's this one. We can actually, start picking out these very, very distant, here we go, these very, very distant bits of light. So this is the picture that led to today's conversation. This is the picture that shows some of these galaxies you see in these enlargements on the right. They're well-formed things. They're not just itty-bitty little dots. They are forming galaxies, but they are really far away, and that means it's very far in the past, which means it's earlier than we thought you could make galaxies.
So you see my cursor? Can you see it on the screen?
No, I can't see your.
So there's right near the top.
Mm-hmm.
There's a little blue point of light, right, like 97% of the way to the top, slightly to the left. Is that the kind of thing you're talking about?
No, we're talking about these little things that are in the boxes. You see these boxed areas? Are you seeing what I'm seeing is the question. Oh, okay, you're not getting the image that I'm showing. Why are you not getting that image?
Oh, I don't know.
Okay, let me stop screen and let me reshare it because it was showing a different screen. And this one is called Webb Images Science. I'm
looking forward.
Here we go. We're going to have it in 1 second. Here we go.
That's going to be good.
Okay.
Yeah, there it is. Okay, good.
And now I'm scrolling through it. Okay,
All
here.
right.
Now here we have the image we want to see. My
Okay.
apologies. I thought it would automatically switch and it didn't. So now we see this image with very, very distant galaxies, those little
Okay.
red thing. And over to the right, in those enlargements, you can see that they're galaxies. They're not just any little spots. And those are, that's like looking out there and finding, a 3-month-old, kicking penalty kicks. And you're like, what the heck are you doing there? You're really forming the real galaxies, but you're very far away. You're really, really, we're looking really early in the universe.
Yeah.
What the heck are you doing there?
So
And
they're so far away and so well formed that
exactly
is not accounted for by the current
Exactly.
theory.
Right.
Yeah.
And it's that kind of discovery that makes science go forward. We learn by getting into environments that we didn't know about before, right? Or that we couldn't test before. Like Einstein's general relativity. I mean, if you look at the ability to observe things in the 19th century, you'd have no reason to think about doing something like that. You get into the 20th century and you start observing stuff, and you go, oh, wait a minute, things behave funky. Lo and behold, general relativity becomes the way to explain it, but you don't know about it until you get into an environment where that's important. Same thing here. Who knew this was going on until you build a telescope that can see it, and all of a sudden you see something and you go, oops, let me, need to think about that. Wow.
So each one of these red smidges could be like 100,000 light years across.
Yeah. Most of these are smaller, but still tens of thousands of light years across, with tens of millions to hundreds of billions of stars. So every one of these blobs is made out of hundreds of millions of stars.
Okay. In the boxes on the right, you can see the expanded view. You can see the galactic shape. What does 1,000 days later mean? It says in the text on the bottom.
So one of the things that we're looking at here is, if you look at the picture at the bottom right and that picture at the top right, in the insets, you're looking at a star that has exploded in that galaxy. You notice it appears in one place and not in the other.
Oh,
And that is how one of the ways that we actually measure distances to things is when we have a star that explodes, we know how bright that gets.
wow.
And that allows you to measure a distance accurately and calibrate what you have. And so these particular galaxies here, they're able to observe a thing called a supernova at tremendous distances.
Okay, the middle photo, the middle image says at 20 something something RLV. Is that when the star explodes?
Actually, that's the designation of that particular supernova there.
Okay.
Yeah.
Wow.
Isn't that cool?
Oh yeah, that's very, very cool.
Is absolutely amazing. And then, you have this continuous collection of absolutely incredible images. And each of them, each of these hundreds of images that's taken is there to look at something in a different way in the infrared with this kind of resolution and at these distances, to start to understand stuff that we didn't know. Because you didn't know it until you started looking, and you go, okay, we're going to look here and see what we see. And there are things you're looking for and you're going to find, and then there are these other things that pop up and you're like, wow, look at that.
As you know, looking at this stuff makes our problems seem, well, pretty insignificant. We are pretty insignificant. Some folks don't like that. I relax a little bit knowing that my situation doesn't matter much. That causes me to relax, actually. I feel a little less responsibility. Like,
right. I mean, I think what it says is, Jim Lovell, the astronaut, who got to go to the moon on Apollo 8 and then was, of course, Apollo 13's commander. He said it was amazing. He said, you could look back at the Earth and you could just cover it with your thumb. he said just how small and insignificant and how delicate the planet is. But he says, on the other hand, think about how incredibly lucky we are that this rock exists, that it has that chemistry, that we get to enjoy our lives because all of this came together the way it did, where it did. I think that's really a tremendous observation.
Yeah.
When you look at it, it's not, okay, nothing matters and, just, forget doing anything, but rather we're significant to ourselves and to everything that's around here because we have this very lucky thing that we shouldn't mess with because this is it.
Which, as you mentioned, is very fragile, and it is such a rarity. It seems too bad to have just wreck it like we have, like we continue to do. But then you take some solace in the fact that, after a certain time, humans will just be gone and nature can have the planet back. That's my theory. What do you think?
Well, I mean, that will ultimately happen in some fashion or other. But you can look at it and say, well, what is it that we're going to be leaving? I mean, how many things will we have? Remember, when we destroy it, it doesn't come back. If you eliminate a species, it's never coming back.
The species is not right.
Right.
But the Earth will again flourish.
Right. Yeah. I mean, yeah, the planet as a whole, all of it will be here. And it'll be here for 4.5 billion years until it gets vaporized. And then it will be the source of material for future planets and stars.
It'll get vaporized by getting hit by something big, right?
No, it'll get vaporized when the sun evolves in about 5 billion years, and we'll have the end of the solar system, and that'll be that.
If it lasts that long, if it doesn't get
philosophical thing to think about, just as you were talking about how lucky we are to be here, but to realize that not only are we temporary, but everything's temporary.
So how will that look down the road in, as you say, 5 billion years when the sun? What will happen?
The sun will swell up as its fuel source changes, as it runs out of hydrogen in the core and starts fusing helium. The outer part of the sun is going to swell up. It will become, even though it will be cooler, it will actually put out more total energy. Mercury and Venus are definitely going to get completely enveloped in this, probably the Earth as well. As the star swells up and becomes what's called a red giant. Then outer parts of the sun are going to float off and the solar system will end its existence. And so, the Earth as an entity, formed 4.5 billion years ago as part of the formation of the sun and everything around us, but it has a finite lifetime. As the sun ends its life, the Earth will end its life.
Yeah. All right. This is great. As this has been. I have one kind of 101 question that I should know, and I probably did know, and I've forgotten. I mean, compared to the stuff we have talked about, this is kindergarten stuff. But other day, I'm looking at the moon, the full moon hanging there in the sky. I think it hit me in a new way. Wow, it is so amazing that just hangs there in the sky. And of course, I forgot. Wait a minute. Why does it hang there in the sky? And all I can come up with is, I mean, there's the tendency of something to fly off, balanced out by the gravity of the Earth. Is that it, or is that?
That is exactly it. The fact that it's moving, and it's moving with sufficient speed that it doesn't fall straight down. It's essentially falling all the time by going around the Earth.
Right.
And it's traveling at a speed that exactly balances the amount of gravity, and it just keeps going around. And if you watch the moon overnight, it moves its own diameter in about an hour. You can actually watch it moving in the sky if you're paying attention. Most people don't spend enough time looking. They look up, the moon's up, and then they go off to what they're doing. But if you watch it, you'll actually see it move through space, which is something you see during an eclipse. You're actually watching the moon move in space, and that's pretty amazing.
So that's how satellites work too, how they hang up there.
Exactly.
But satellites, they run out of gas. They crash down sooner or later, right?
It's not because they run out of gas.
I don't mean actual gas.
Right.
Inertia or whatever.
Well, actually, it's not that they run out of it. It's that there are small amounts of gas up there. The Earth's atmosphere doesn't just stop. It's not like breathable and then not breathable. there's small amounts of gas up there, and you have a little bit of wind resistance,
Oh.
which is why you don't fall right away. But over a span of many, many years, you keep losing a little bit of speed, and eventually you're not moving fast enough, and down you come.
And the moon is out beyond the gas, and that's why it doesn't slow down and crash
That's right.
down to the Earth.
Exactly.
Wow. Well, I guess we've covered a lot today, huh?
Absolutely.
What projects are you involved? And talk about the projects that you're involved in again, and maybe any events that are happening or things conferences that you're going to, etc.
So the big thing is the upcoming total solar eclipse. It's going to be on April 8th. It's going to cross the United States. I'm very involved in getting everybody prepared for that. I'm giving talks and workshops and training programs. We're doing programs for teachers. I'm speaking at a library this evening, trying to get everybody prepared for this truly once in a lifetime event. You know, I live in New England. The next eclipse that'll come to New England is in 2079. It's not for another 55 years. I mean, some of us are probably not going to be here for that. So it's really an opportunity. And as I said, you actually watch the moon move in space as it covers the sun. When it covers the sun, the ground goes completely dark. We see the corona, the atmosphere of the sun. Animals go to sleep. The temperature drops. It's one of the most amazing things you can experience. It's going to cross the U.S. from Texas to Maine on April 8th. So make sure you go and see that. Definitely something to make sure that you see. And that's just one of the activities I'm involved in through our program, Mountains of Stars, where we try to do exactly what Bradley was talking about, get people to understand where this Earth came from, where we fit in, and to take care of things better, because if you're out there looking at space, you have a much better sense of that. So it's a very big part of the work that we do.
Is it kind of remarkable that the moon is the size and the distance such that there's just that little thin corona around it when it's in front? Isn't that kind of...
It's amazing.
It is.
It's a complete coincidence.
It could either be a little dot in front of the, or it could completely block it out. But no, it fits so there's just this little corona around the edge.
Exactly.
If it were further away or bigger, you wouldn't see that.
Exactly. You're exactly right. It just coincidentally, it and the sun are proportionally the same distance. So the moon is 110 times farther away than its size. The sun's 110 times farther away than its size. So they look the same size in the sky. Complete coincidence. Doesn't have to be like that at all, just as you said. Totally amazing.
Hold on, that's not good. My phone was ringing. I don't know if you guys can hear that, but it's not anymore. All right, then. Thank you so much. This is pretty amazing, right, folks? How can people get involved with Mountains of Stars or your other organizations? Also, the Dark Skies Project.
So to get more information about what we're doing, and we have lots and lots of information. Our website is mountainsofstars.org. And Bradley can put that in the listing for this so that you can go to it directly. Mountainsofstars.org. We have webinars and podcasts, recordings of a lot of the things that Bradley and I have done over the years are there. There are TED Talks, videos, books, references, all sorts of great things, lots of astro pictures, great stuff there. So please take advantage of that. And one of the things that's linked there is the International Dark Sky Association, Dark Sky International, where you can learn about how to control lighting that will actually make your life safer and healthier and save energy. And that will help bring the stars back too. But it's really about using energy wisely. So a lot of that information is there. So please check that out.
I did get one last question. Isn't our moon moving further away from us little by little?
In fact, it is. And that's because of tides. The fact that, the moon and the sun together pull on the water. And that's why we have high tides and low tides. And because the Earth spins faster than the moon goes around, that lump of water is actually a little bit ahead of the moon in the orbit. So it's actually making the moon go a little faster and the Earth go a little slower. So days are actually getting longer by fractions of a second. not a lot for you to measure, but we can actually measure the fact that since the moon is speeding up a little bit, it's getting about that far, literally, see my fingers, about that much farther away from us each year. So over many tens of thousands of years, it eventually will be too small in the sky to completely cover the sun. So we're super lucky to be living right now when it's just big enough to do it. Because if you come back in a few tens of millennia, it will have shrunk in the sky just a little bit, just enough that we're going to lose total eclipses.
It amazes me that you know so much, and I appreciate you sharing it with us. Thank you so much, Doug Arion. Appreciate it.
Thanks so
Share
much.
this, folks. You know people who will love this. Please share it. I know that I'm going to share it, and I know that Doug shares it. Thank you, and we'll end the live portion of this broadcast right now, folks. Thank you very much. But